What does that mean?
I should have expected this question. um,
Welcome to Matter Over Mind. My name is Stephen. I'm an organisational psychologist, and today, as always, I've got my favourite son-in-law Thomas with me. Say hello, Thomas.
Hello, how you doing? I'm the physicist of the duo.
You are indeed.
Um,
You're doing
yes,
a PhD in plasma physics. Am I
yes,
right?
indeed. Yes, experimental plasma physics at the University of Oxford. So it's very exciting stuff.
Perfect. It is. You've just been giving me a bit of an update. We won't talk about it just yet because there'll be updates to come, I'm sure. But suffice to say, you're progressing, and it's all very exciting.
Yes, indeed. Stay tuned, folks, for
Stay
that.
tuned, indeed. More teasers. Right. Okay. One of the things that one or more of our listeners have asked for is stuff about the Higgs boson. And in fact, um, I've been wanting to talk about this topic for ages, and you've kind of been saying, yeah, it's quite complicated. Um, and kind of putting me off, I feel. But it's the standard model of particle physics is the topic for today, isn't it, Thomas?
Yes, yeah, we will touch a bit on the Higgs boson at the end, but particle physics, as it's actually done on how you learn it, is quite different to how it's portrayed in sort of pop science and what have you. So hopefully, I'll shed a little bit of light onto that today.
Good. Okay. So I suppose that the first question that I've got is a really simple one. It is, what is particle physics? When I was at school, I remember talking to my physics teacher about this. I was into physics, and I remember talking to him about the atom, and he was saying, well, you know, because we learned the classic sort of atom structure of the electrons around the proton and neutron and all that, and you know, that kind of was nice and easy for us to understand. And he said, well, in reality, it doesn't, you know, we don't really think it looks like that. You know, it's sort of more of a cloud of something, he said, which I didn't really understand at the time. I still don't know what he meant by that. But he seemed to be a bit skeptical about it as well. And we are going back, 40, 50 years. So it's interesting the state of knowledge at that point. Obviously, we already knew about quantum physics and so on, but I'm not quite that old. But still, I think we've got a better handle on it now than we ever had. It just seems so hard to understand. So what are we talking about when we talk about particle physics? Because, you know, okay, you've got particles, atoms, and then inside the atoms, you've got more stuff, more particles, and then you got more stuff. I don't know. What is it? What is particle physics?
Okay, so I guess there's a hierarchy to these things. So
Yeah.
the obviously we have the macroscopic scale, which is us, and then you've got chemicals and so on and so on. But of the sort of more fundamental building blocks, obviously most people know, or at least have heard the term atom or atomic physics. So atoms are, I guess, the biggest constituent once you get to this sort of scale of stuff. So atoms are a collection of nucleons. So it's a nucleus surrounded by some electrons. So that's atomic physics. Any physics to do with a nucleus with bound electrons to it. So the clouds that you're kind of mentioning. We can do a separate episode specifically on the quantum mechanics of atoms at a later date. But for now, you have a nucleus surrounded by bound electrons. That's atomic physics.
Okay.
So what happens now if you strip away all the electrons, all that complexity, strip that away, you're left with just the nucleus. So that's nuclear physics. So how specifically the nuclei of atoms behave. And then you zoom in a bit more, and then to look at the sort of constituent parts of the nucleus, and that's where we're in the realm of particle physics. So it's subatomic, if you will.
Okay. So these are the constituents of protons, neutrons, and neutrons. Is that right?
Yeah. So protons and neutrons make up the nuclei of atoms, but there's also constituent pieces to protons and neutrons.
Yeah.
So in terms of what particles there are, there's a really good little chart on Wikipedia actually that has a breakdown, because there's two kind of main classes.
That in front of me. Hmm.
Yes, is it the one with you've got fermions and bosons on the
Yeah.
left and right? Yeah. So
Yeah.
so the I guess protons and neutrons are the biggest particles, if you will, um, with some caveats. So I'll explain a little bit. So we've got
Okay. So before we
yeah.
do that, actually, if you're listening to this, well, if you're listening to this, if you're not listening to this, then obviously that's a stupid comment. If you're available or if you're able to call up Wikipedia, then that illustration on there, I'll put the link on the show notes, and you can literally look at the diagram we're talking about. So that might just help a little bit if you want to do that. It's not a training course, but it might help to understand. So you can click on that and follow along with us as we're talking about this. So we're looking at it now. We're looking at this model with the various different particles. It splits. If you look at along the top there, we've got three generations of matter called fermions,
Mhm.
and that includes quarks and leptons. And then we've got interactions or force carriers, which are called bosons, on the right hand side. And that includes things called gauge bosons and scalar bosons. So that's what we're looking at. Take it away, Thomas.
Okay, so there's a lot of detail here that, for the kind of point of this discussion, are too much detail. Like talk
Okay.
about half integer spin and that kind of stuff. That won't be covered, or at least I'm not
Okay.
going to be talking about that. So
Okay.
you've got your fermions, which are your kind of regular matter. So you've got from your fermions, you've got your leptons, and then you have what are called your baryons. So your baryons are your sort of protons, neutrons, and there's a few others. And the protons and neutrons, are made up of quarks. So you've got six flavors, they're called, of quarks: up, down, strange, charm, top, bottom. And that's what they are. So and these sort of protons and neutrons, for example, they're made up of three quarks, a combination of three quarks. So protons like up, up, down, neutron is down, down, up, and then you've got some other colourful particles there too. So the quarks in this case are the fundamental building block of the baryon. On the other hand, we have the leptons. So these are your electrons, your your muons and your tau, which you probably won't have heard of, but electrons you would have heard of, and then your neutrinos. So these are leptons, and these are also fundamental. So there's nothing below. There's nothing that makes up an electron other than itself. So there's no, unlike the proton, which is built up of quarks, leptons are fundamental. Right. So those are
What
your sort
about?
of
Sorry to interrupt. What are quarks? Not fundamental then.
quarks are fundamental. So
They
quarks
are
build up
fundamental.
your baryon. So three
Okay.
quarks to a proton, three quarks to a neutron, and so on and so forth. There's a few other baryons there. So
Baryons are, because that's not on this model. I can't see the word baryon anywhere.
baryons are your protons and your neutrons, and there's a few others.
Okay.
So it's just
Okay.
a yeah.
Okay.
There are other diagrams which kind of have different
Okay.
terminology, but yeah. So you've got your leptons and your baryons. Your baryonic matter is comprised of quarks, and your leptonic matter is their fundamental. So fine. So that's your kind of regular matter, your regular stuff. On the other side, you have your bosons. So yeah, these are charge carrying particles. Force carriers. So what that
Hmm.
means is, on a fundamental level, interactions don't really occur by a particle colliding into another particle like a billiard ball. That
Hmm.
doesn't really happen. There's actually a good diagram in my A-level physics textbook that kind of explains this reasonably well. So
Good.
imagine you're a particle, I say a proton, and you're standing on ice skates on the ice stationary. And I'm
Okay.
skating across the ice, and I'm holding a bowling ball. As I travel past you, I toss the bowling ball at you. You now
Yeah.
skid along. So the bowling ball there is the
Uh,
is the boson. It's the interaction particle.
right.
So you may have come across the term virtual particle or virtual photon,
Yes.
for example. That basically, that the virtualness of the particle is because it only really exists to mediate that interaction. Outside of that, it doesn't really exist. It does exist physically; it is there, but it only exists for the time that that interaction occurs. If that makes any
Oh,
sense.
that's really helpful. So before we started this conversation, I was saying that for some of our listeners, they may be much more advanced in maths than me, so they may get much more advanced stuff out of this. But for me and listeners like me, It's just trying to find one or two useful things that, oh yeah, right, I get that now. And that's really useful because I've heard of these virtual particles before, didn't really understand what that meant. So they're not really virtual, are they? They do exist, but as you say, they only exist as a way of interacting with another particle. So they're kind of like the middleman,
Yeah,
I
yeah, yeah,
guess. Okay.
yeah, exactly. And you can get, I mean, with kind of all these things, you can get. So I mentioned I wasn't going to talk about spin, but for example, fermions are half integer spin, which basically means half, 3/2, 5/2, and so on. And bosons are integer spin, so integer is just a whole number.
Mm.
You can get, for example, composite bosons. You can get collections of particles that collectively make up an effective boson. So when you group together a bunch of types of particles, you could in principle have an integer spin total, therefore it behaves in bulk as a boson. So that's why maybe you've come across Bose-Einstein condensates, which is just it's a macroscopic quantum wave
Okay.
function by supercooling a bunch of composite bosons. We won't get into that now. We can do a separate episode on more quantum stuff. But that's just a thing that can.
Hello, just a quick interruption. As you can see, I'm in editing mode at the moment. I'm just editing one of the latest podcast episodes. Just a quick reminder to subscribe if you're watching on YouTube. Maybe leave a comment. These are the things that make a difference to how many people get to hear about it, and we want more people to know about the Matter Over Mind podcast. If you're listening on a podcast app, same goes for that. And also, why not let people know? Just send them a text or let them know. If they're into science, then this is kind of a good podcast for them. So that's the first thing. Second thing, we've been asked to have a question and answer episode where we just answer questions that you have. So that means we need questions. We've already got a few in our locker. So please send your questions to us either on the free Facebook group, which I've talked about before, or you can leave comments on the podcast itself. Just let us know what sort of topics are you interested in, and also specific questions. You know, if you've ever thought about this or ever thought about that. I mean, ideally related to psychology or physics. If there's other questions you want to ask, that's fine, and we'll see if we can research some of those things. Maybe even get the odd guest on from time to time. Okay, so that's it. Thank you very much for listening. Back to the podcast. Okay, so let me just check my understanding on this. So we have these things like photons, which are we call bosons, and they
Sorry,
are
protons.
protons. Sorry,
Yeah.
protons. These are things called bosons. Correct?
No, protons are fermions.
All right. Okay. Okay. So we have. I'm looking at my diagram here. Right. Okay. So 3 generations of matter fermions. Where does it talk about protons on here? It doesn't, does it? We haven't got a picture of protons on here.
No. So what will happen? So it shows you the quarks. So if you have
Okay.
quarks, you know
Yeah.
the quarks make up protons and neutrons and so on.
Right. Okay.
So if there's quarks in that part of the diagram, that must be to do with protons and neutrons.
Right. Okay. So quarks make up protons and neutrons.
Yeah.
And quarks are fundamental. They are. There's nothing makes up quarks
Not that we know of. No, that they're
that we
for
know
our
of.
current
Yeah.
theories, they're
Yeah.
fundamental. Yeah.
Okay. And then we have leptons, such as the electron, which obviously everybody knows that. I think most people have heard of neutrinos as well.
Mm-hmm.
And these are leptons, and they make up what?
Well, they're just kind of their own thing, but they are
They're their own
fundamental.
thing.
Yeah.
Okay.
Yeah. Yeah.
So they're their own thing. They do their own business. They don't make up anything else. And then we also have these force carrying particles that your illustration of the passing the ball between, or passing the thing between ice skaters, is a good way of explaining that. Okay, so that's what they do. They enable interactions to happen between particles.
Yeah. Exactly.
Okay.
Cool. Yeah.
Cool. So what are we talking about there? You know, so the way I describe that sounds a lot like, these are constituent parts of things that make up other things, and that's how a layperson's mind will work. It's, okay, we've got this. This is made of something else, and these are the building blocks of that. Um, but is that the right way to think about it? Because you said they're not really particles at all. Is that right? How should I think about these things called quarks and leptons?
So it's pretty tricky actually. I did have
Mm,
when I was studying particle physics in my undergrad, I thought up a cool little visualization in my head, which
mm,
probably isn't particularly useful unless you're specifically studying it.
okay.
But basically, our current models describe them as fields. So we've kind of mentioned a bit about field
Mm,
theory
we
in a
have.
previous episode. So and the particles are excitations in that field. So I guess to give
Got you. Yes.
a bit of a more tangible picture, imagine you have a bed sheet. The
Mm,
bed sheet is the field. Say call it the electron field. Say the bed sheet. If I pinch the bed sheet, there's going to be
mm,
a little nodule on the bed sheet.
mm.
That's a perturbation on the sheet because it's a
Yeah.
deviation from equilibrium. It's a bunching of the sheet. So if the sheet is the electron field, that bunching of the sheet is an electron. That
Yeah.
excitation in the field is the electron,
Yeah.
or
Yeah.
in the
Yeah.
proton field or the quark field or whatever.
Okay.
Any
That's
arbitrary
good.
field, the excitation is the particle.
Yeah, I remember we talked about that now. I'd forgotten about that. And that was a useful way for me to understand that. Great. And there's kind of fields of all sorts of things. And electrons are just one example. Obviously, the things we've just talked about, the particles we've just talked about. So in that case, then there would be I don't know what, a neutrino field doing the same thing, essentially.
Yeah, exactly. So these kind
Okay.
of fields, I guess the way to think about it is they're infinite in extent, and they kind of
Mm,
phase through each other because they can
mm,
interact in some way. So it's kind of hard to visualize when you get to field theory because everything is just an infinitely spanning field that is
mm.
simultaneously meshing through each other while also
Yeah.
engaging as well. But yeah, the idea that the electron field is just a sheet, and the bunches in that sheet are electrons, or the proton field is just a sheet, the bunches in it are a proton. That's the kind of
Yeah, and I don't think that's that difficult to understand. I like that. I think that makes a lot of sense, and yeah, that works for me. So okay, I've got you there. Good,
Mhm.
thank you. Um, all right, so where do we go next then to understand this topic?
Okay. So the fact that we're talking about fields means we
Hmm.
probably have to be talking about Lagrangians. So again,
Our
it's
favourite.
our favorite, the Lagrangian. So this is
All
again
right.
an episode that we've done before, but
Yeah,
I'll kind of refresh listeners that
please.
perhaps.
Yeah, please
Yeah.
do. Yeah, yeah,
So a Lagrangian, a way to think about it is an energy balance. So
yeah,
it's within a system, it's the difference of the kinetic portion of the system versus the potential portion of the system.
yeah.
So, as an example, if I hold this little pot above the table, it's got some gravitational potential energy, as in, I know as soon as I let this go, it will start accelerating downwards and it will gain some
Hmm.
energy. So it's potentially got some energy, I guess you could think about it. So
Mm.
that's gravitational potential. If I drop it, it will start moving. Therefore, that potential energy is being converted into kinetic energy. So there's a balance between potential energy or stored energy and kinetic energy. So a Lagrangian simply is just a balance of that. It has a kinetic component and a potential component.
Mm.
Fine.
Yeah,
And Lagrangians are used in what are called actions. And actions, you can think about them as trajectories through your space time, and unless kind of interacted with externally, when you minimize an action, what that determines is the path of shortest proper time. Again, kind of some jargon that we've defined previously. So what that basically means is the path of least resistance, or
mm.
if you let something travel through sort of time and space, it will take the path that uses the least energy. It can only use
Yeah.
as much energy as it has. Yeah.
I think that again, sort of instinctively makes sense. Okay, so the question that I was left with when I refreshed my memory about the Lagrangian was, why is that better? Why does that make more sense to describe the path of something than what I'm used to, which is something around acceleration or direction, or so it's here at one moment, then it's somewhere else, therefore it's taken a path from there to there. That's the way I think about any action in the world. It's things are happening within space and time. But the Lagrangian is trying to do, I suppose, is doing the same thing but better, obviously, because that you use it, that's why you use it. So why is that better? Why is it to describe, why is action better described as the Lagrangian rather than the way that I've just described it?
Okay, so yeah, that's a good question, and it's a question I also had when I first started learning
Okay.
this stuff. Because one of the first things you do when you learn Lagrangian mechanics, because from the Lagrangian you can derive Newton's laws of motion, so
Yeah.
they're kind of one and the same
Okay.
thing. And when you first learn it, there's a classic ball rolling down a hill problem. Fine, so you can
Yeah.
do that with forces. You can say, okay, well, gravity is pulling it down. It's on an incline, so that's going to drag it to the side, and then you can kind of work out some stuff from there. So that's one method. And then you learn to use Lagrangian mechanics to solve that same problem. It's a bit of a sledgehammer, to be honest, because you, you don't need it, but in principle
Yeah.
you can. So that system's kind of easy. You could make the same argument. Why not just think about forces pulling it instead of energy balance? But suppose now you had a little particle attached to a string in a complicated system of pulleys and other weights kind of balancing it. You'd have to, doing it the sort of the classical method that you've described, you'd have to work out, okay, what force is pulling what where. You'd have to count all the forces, make sure they all balance each other out, make sure what they're doing before you could discern how fast or slowly, or maybe not at all, the ball on the string is moving. Whereas if you use Lagrangian mechanics, you can look at the system. Okay, everything's stationary. Cool. We know the kinetic energy is zero, which means the potential energy is whatever it is, right? So you've kind of just snipped away almost all the complexity of that situation.
Okay.
So it's that kind of
Okay.
idea. I mean,
Yep.
like everything, there are some caveats, but essentially, in some cases, resolving forces becomes very cumbersome, and eventually, it just becomes a fruitless task rather. Whereas looking at just the energy of the system overall can tell you
Got
just
you.
as much.
Okay. Thank you. Useful. Okay. Good. Okay. So we've been reminded of the Lagrangian, which, by the way, is our most popular episode of last season. People loved a bit of Lagrange. Um, so yeah, good on you. Okay, what's next then?
Okay, so when we have Lagrangians or Lagrangian mechanics, we can't forget our friend Emmy Noether and Noether's theorem. So I don't know if you recall what this was, but this was essentially saying, yeah, let's see. Do you remember what Noether's
No,
theorem
I
is?
remember it's a woman, isn't it?
Yes,
A
yeah, yeah,
female scientist, which is unusual in physics because of obviously the society in which physics was developed. There aren't that many women mathematicians, I guess. Of the, what was she, 18th century, something like that.
yeah, something like that. Yeah.
So I can tell you that, but nothing else. I'm afraid. Sorry.
Okay, so what she proposed, or I guess what she proved, was for every symmetry a system has, there is an associated conserved quantity. All right. So
Okay.
just to kind of remind the listeners of some symmetries. Obviously, you've got if you have a square and cut it down the middle, it's symmetric. Fine. Okay,
Yep.
that's an easy one. Suppose now I have a disk, so I have a circle. If I rotate that disk, you could say it's got rotational symmetry. The disk doesn't appear to change if I rotate it any, right? If I put a little cross on the top of the disk and then rotate it, it's now no longer symmetric in the same way because I now know that I've rotated it, right?
Uh-huh. Yeah.
Fine. Similarly, there's stuff like translational symmetry. if my system's unchanged when I move it from A to B, then that can tell you about the momentum. You can say, okay, the momentum's conserved because translationally nothing's changed. Therefore, it probably hasn't moved. Or there's temporal symmetry. If a system is unchanged over time, energy is conserved, for example. So there's some examples of symmetries and their corresponding conserved quantities. Okay, so and you can only really make those arguments when you're dealing with Lagrangians and energy balance for
Okay.
a bunch of mathematical reasons, which I won't get into. So that's the kind of the underpinning. If you have Lagrangians, you're probably thinking about Noether's theorem. And it turns out that sort of Lagrangian mechanics and symmetries are the language of particle physics. It wouldn't really exist without this. So that's the kind of state of play, and that's probably why when you hear about particle physics and pop science, you may get some discussion of quarks and neutrinos and electrons and so on, but that's kind of where it stops. It's kind of a classification exercise. It's just an accounting. There's this particle in this one, then this one, and then it kind of stops there.
Yeah.
It's probably because discussing, local and global symmetry breaking is a little bit complicated.
Yeah, well, that is it. It's just not the way our mind works. We think about bits of stuff that are made of smaller bits of stuff. So once you get past that, then it's really hard, I think, for most people to understand. All right, so when we're talking about symmetries, what relationship do symmetries have then to this discussion about particle physics? What does that tell us, I suppose?
Okay, so I've kind of sketched up a little bit of an example to kind of help us understand, how this could be used in principle. Now, again, this is very condensed, and there's a lot of caveats, underpinning this. But just for argument's sake, this is a rough idea. So, if I said to you that charge is a conserved quantity, so if you have a collection of, say, electrons have a negative charge, and then something occurs, and then the output is some other stuff, it's a fair comment to say the charge is conserved. That the charge on the left-hand side before the interaction is equal to the charge on the right-hand side, right?
Okay, so just before we go on, as this is a fundamental episode, I'm going to continue to ask some stupid questions. and the question that suddenly occurred to me is, what is charge? Because we've talked about fundamental particles. Literally, there's nothing more fundamental than those things. So when we talk about a fundamental particle having charge, what does that mean?
I should have expected this question. So I guess charge
is it okay, so here we have, I suppose, one of the philosophical or ontological questions about this topic, which is like when we say that a particle has charge, or a particle has spin, is it the same sort of thing? It's kind of an arbitrary label that is given to something that we don't really understand. Is that really the case? That, okay, we're saying this has something called charge, but do we know what that is, or is that just a label that we give it because that makes the maths work? And I suppose that's one of the criticisms people have of this whole field. But am I talking rubbish here?
I mean, I guess to some extent, yes, it is an arbitrary label, like spin or charge or chirality or color or whatever, right? The color, I mean, in the color charge sense, not color as in blue. Yeah. So charge, if something has a charge, it means it can interact with the electric field.
Okay.
So okay. I guess that's would be
great.
my answer.
That's an easy answer. You could have given me that straight away. I would have been satisfied with that.
Yeah, I was just having flashbacks to undergraduate when everything has to be so very specific. I didn't want to misspeak.
Yeah.
um,
Yeah. Okay. Okay.
okay,
Okay.
so
I'm with that. I'm up for that.
electrons have some charge. They can interact with the
Yeah.
electric field. So suppose a bunch of electrons start bobbing around. They interact in some manner. They kind of collide against each other and so on. So that's the interaction when they're kind of doing stuff together. And then
Got
the
you.
end result is these particles. They're kind of still there, but it's post some interaction. So say you got two. They come in. They kind of bounce off each other. So I'm going to make the bold claim that the charge of the system before they interact is equal to
Yeah.
the charge of the system after they interact.
Okay.
So
Yeah.
that's probably a fair, a fair thing to say. If I roll a little ball across a desk, I can say there's one ball on the right hand side of the desk. It rolls. On the left hand side of the desk, there's still one ball. The number of balls is conserved. The number of charge is conserved. So that's my argument. Okay.
Okay.
So, okay. Yeah, okay. So that is, you could argue, is a global symmetry. The symmetry there is charge is conserved across this system. And global just means, the big picture. So I'm not looking at the black box that was the interaction. I'm just saying overall. Fine. Okay, so the way this discussion goes is you can introduce a constant phase shift to the electric field, right? So I'll kind of already, I guess that's probably quite technical. So
Say that again.
So I suppose I introduce a phase shift in the electric field. Kind of like imagine you've got an AC current. You've got a sort of sinusoid, or literally just like electricity. You've got a bobbin. So if I have a sine wave, I can phase shift it to the left or right. So I can so instead of a sine wave, you get a cosine wave, for example. So it's just shifted 90 degrees to the left or right.
Okay.
Does
So
make
that
sense?
didn't mean anything to me. So let's go back to the field. So we have a electric field, and you are saying that there is a phase shift in the electric field.
Yeah.
What's a phase shift?
Okay, so imagine you've got a surface with a bunch of waves on
Yep.
said surface.
Yep.
Actually, no. Maybe better is in terms of sound. So you've probably heard how some soundproofing works. The earphones.
Yeah.
You listen to a frequency, and then the kind of computer in the headphones plays the anti-frequency,
The
if you
opposite.
will. And
The opposite.
it cancels it out.
Yeah. Cancels it out. Yeah. Clever. Very, very clever technology.
Yeah. So that's phase shifting the incoming signal. So the sound comes in, the computer registers its frequency and so on, and then it shifts it in your phase space, in your frequency space, and it shifts it by a period such that the waves, now the troughs, match the peaks of the other one.
Yeah.
And when the troughs and peaks line up, they cancel each other out.
Yeah.
So that's what's called a phase shift. I'm shifting my frequency such that when the other frequency comes along, they're out of phase, and if they're perfectly out of phase, they'll cancel each other.
Oh, okay. That's a phase shift.
Yeah.
Gotcha.
Yeah.
Okay. Good. Yeah. Thank you.
Fine. So, okay, imagine you've got an electron whizzing around, and you have an electric field, and this electric field has some waves like that. Well, the electron is going to react to the waves, right?
Yeah.
Because it has charge, so it's going to interact with the electric field. Suppose now I introduce a phase shift. So I shift the waves. So instead of having a peak, it may have a trough, say. So I've shifted the phase of my electric field. Fine.
Yep.
And suppose this is constant across all space and time. I've just taken the wave, I've shifted it, and if you zoom in, it's the same phase shift as over here as it is over there. It's a global shift.
Okay.
Right?
Yep.
Okay. So let's see. So if you do this, you can show that the Lagrangian that describes the dynamics of the electron remains unchanged. There is no change in the Lagrangian if you introduce a global phase shift in this system. Right? So basically moving the pattern of the wave seemingly doesn't really do anything. Right. So what you'll do is in your equation, you'll have your Lagrangian, you'll have an equation that describes it. And you can basically just multiply each term by a factor, and that factor accounts for the shift in phase. Fine. And what you can show is the Lagrangian after doing this shift is exactly the same. The form of the Lagrangian is identical to how it was before. With a caveat, there will be a prefactor. So that prefactor will be some scaling. So the Lagrangian might be slightly bigger or slightly smaller, but the way it behaves is the same.
Okay. And you gave me a really cool little example of that, or an illustration of that, about eating your tea or your dinner.
Yes, yeah. So before I eat my dinner, I am Thomas. I then introduce an interaction, a phase change. I eat my dinner. After the dinner, I'm a little bit heavier, so that prefactor's there, but I'm still Thomas. I'm still the same person, right?
Yeah.
The way I behave and the way I act is unchanged, even if there is a prefactor, even if I am a bit heavier. Fine.
Okay.
So that's the kind of example that, your Lagrangian will be the same, scaled a little bit, but the form of it is the same.
Yeah.
Fine.
Yeah. Yeah.
Okay. Cool. So that's fine. But suppose now, so that's a conservation of a global symmetry. The conservation there is I've introduced a global phase shift. The entire system has shifted in phase, and globally there's no change. So basically that says the charge before the interaction is the same as the charge after. Okay, cool. Okay, so now let's get a little bit more specific. Suppose I don't have a uniform shift. Suppose locally on small scales there is some variation. Right? Can the same be said? Is the symmetry still true? Is the system still unchanged under a local change? So if I get a bit more specific. So it turns out the Lagrangian now is different. So it's no longer the symmetry has been broken. In this case, the gauge symmetry is called.
For that localized region, is that right?
Yeah, exactly. Yeah. So that's kind of you've shown globally on the bird's eye big picture view, nothing's changed. So now you zoom in a little bit and you think, oh, actually, when I zoom in, that's no longer true. There is a difference now between the Lagrangian afterwards. The physical form of the Lagrangian is different.
Yeah.
So you've said you've broken this symmetry. There's a symmetry break here. Something's gone wrong. And why something's gone wrong and why we know something's gone wrong is because the initial, I guess, statement that charge is conserved. Charge goes in, something happens, charge comes out. It's the same charge. So why is it on small scales that's not true?
Okay.
Something additional must be there to account for
something.
We're missing something, exactly.
Yeah.
So we've called what is said promoted our global symmetry to a local symmetry, and that's because we're now looking a little bit fine tuned through the
more granular.
Granular through the microscope, and we've noticed actually this statement doesn't hold across all scales. So let's kind of investigate what's going on here. Fine. So what you can do in this case is it turns out if you introduce what's called a gauge field, which I'll somewhat touch on, you introduce basically an additional term to this transformation. With this additional term, then the Lagrangian remains unchanged. So it's only when you introduce this gauge field. So this is why it's called a gauge symmetry. A gauge field, there's no easy way of explaining it, but for those interested, it's introducing a scalar gradient to your scalar field. So I won't
Maybe
get into
we'll come back to that.
Yeah. So, so we've said on a big global scale, we're happy. Once you get more granular, there's a problem. So you introduce this gauge field term to such that now the Lagrangian is unchanged under this transformation. Okay. So the analogy I've added then to this is still with the me eating dinner analogy. Before dinner and after dinner, I'm still me. I'm still the same person. But suppose now we get more granular. Suppose now instead of just saying I'm eating dinner, I'm doing something while I'm eating. I'm eating dinner. I'm walking around and talking and messing about.
Hmm.
Well, now when I finish my dinner, because I've been walking around and doing stuff, I've not been settled. After dinner, I feel a little bit poorly, right? Because I've been messing
Okay.
around.
Okay.
So if I wait enough time, I start to feel a little bit better. The nausea of me running about is
Hmm.
kind of relaxed. And then I'm at the same state as in the global case. After
Okay.
dinner, I'm still me, just a bit heavier.
Hmm.
But that additional kind of fiddle factor, if you will, of
Hmm.
me being poorly needs to be accounted for. That's only
Okay.
that me being poorly only exists on the small scale because I've explained to you I've been running about and doing some other stuff.
Yeah.
So
Yeah.
that's kind of a way to think about adding this gauge field. We're not really adding
Okay.
anything. It's already there. It's just a bit more specific. You
Yeah.
need correction terms that can kind of balance each other out
Hmm.
on this
Yep.
local scale. Fine. So, so what you've done there is you've introduced an additional field to kind of, I guess, to conserve the symmetry across all scales.
Hmm. Hmm.
So this symmetry is called a U1 symmetry, unitary symmetry with. There's a whole thing called group theory that if you're interested you can go away and read up because that's kind of also important for particle physics, but it's too in the weeds for this
Yeah. Yeah.
podcast.
Yeah.
So anyway, so when you conserve the symmetry, when you introduce this gauge field, it's now symmetric globally and locally.
Hmm.
What this leads to is what's called QED, quantum electrodynamics. So
So that again, quantum electrical dynamics or electric dynamics?
quantum electrodynamics, or QED.
Electrodynamics. Okay.
Yes.
Yeah. Okay.
Yeah. So this is kind of the simplest of the field theories. It's kind of the first thing you learn. The math is quite straightforward once you've got enough of a background, that is, to kind of understand, and it kind of neatly falls out. And what this is kind of telling you is this additional thing, this gauge field you've added in. It turns out in this theory anyway to be massless, and it has the same properties as field strength, this electric field strength. And if you'll again remember back to episode 1 of season 1 when we talked about light, electromagnetic fields is light. So
Hmm.
what we've discovered here is the photon. So the electric field, when electrons or electric charges get accelerated or decelerated, they emit a photon. So they interact with the electric field via the gauge boson that is the photon. So that's the
Wow. Wow. I never thought we'd have discovered a photon today.
yeah.
Okay, that's really interesting, though, isn't it? So what emerges from this maths of trying to balance out the symmetries is a real thing that we can then sort of test for or create experiments to confirm, I suppose. And is this the same principle for other particles? Is this essentially how we discover other particles?
Yeah, pretty much. I mean, there's a lot of symmetries. Obviously, this is this particular one of a phase shift in your
Yeah.
in your frequency. That's quite a straightforward one to kind of get your head
Mm.
around. You can kind of imagine that. There are some more complicated symmetries, a bit more abstract. That I would be impressed if someone came up with an easy to understand analogy
Mm.
without relying on maths. But there are a
Mm.
bunch of them. So for example, these symmetries led to the discovery of quarks. You have there's actually, because of these symmetries, there's actually a maximum number of quarks that can exist because of how
What
these
in the
symmetries.
universe?
Yeah, just total that there can only be.
Oh, I love that. Okay, so how many is that then?
I think it's like. Well, I think it's six, and then the other
Six?
slots.
What? Six? Six quarks?
Well, sorry, six types of quarks. I
Oh,
should say.
okay. Oh, okay.
Yeah. So, yeah. So, okay. In the same way, there are six types of leptons. You've got electrons, muons,
Okay.
tauons. Yeah.
Okay.
So not six. there'll
in
be
total.
nothing.
I thought you were going to tell me how many quarks are in the universe. I was going to
No,
be
no,
really impressed by that.
no. So there are 6 types of quarks, or 6 flavors of
Okay.
quarks.
Okay. Okay.
So in this kind of
Okay.
grid, when you conserve these symmetries, you get kind of a grid, and 6 of those slots in that grid are taken up by quarks, and then a few other slots are taken up by some other stuff. So that's kind of how you kind of build up this picture. By conserving
Okay.
certain symmetries, it kind of tells you, something has to be here in that slot. And then that thing in that slot, it'll be a piece of math in the Lagrangian, and with that will come some physical properties. It does it have mass? Is it charged? What's its color charge, for example? What's this?
Okay.
What's that? And then those are some physical attributes that you can now then search out for in your hadron collider or whatever.
Okay. So I didn't expect to get this far really in this episode in terms of understanding how they're kind of made up, or how they're discovered. This is how they emerge through these symmetry groups. Um, so how many of these different groups are there then? So we've got the symmetry you've described as U1 symmetry, which is the one you've described of the gauge field. Um, is that it? Does that give us everything?
So in terms of how many groups, and this is, if you ever learn this, I guess more formally, you'll be very frustrated because anytime anyone shows you a group, they'll always hit you with this is a representation of that group. And then actually pinning down what the actual group is, no one will tell you. No, this is a representation of the U1 group. Oh, okay. So is it this? Well, that could be a representation, right? So, but in terms of groups that give us particles, there are potentially more, but I guess the big hitters, you've got U1, which tells you your electric, your photon and electric field and stuff. Okay. Then you've got your SU2 cross U1 symmetry. So this is your electroweak symmetry. So this gives you your weak nuclear interactions. So this is when your nucleons, your protons and neutrons are inside the nucleus, they interact via the weak force. So it's one of the fundamental forces of nature, the weak. You also have the strong nuclear force. The strong nuclear force actually was extremely complicated, and I don't really remember anything about it. It was one of the last things we learned when I did QFT, and it was mind-bogglingly complicated.
So you can think it's one of those things. Even Thomas can think to himself, "Great, I never have to think about that again."
Exactly.
Okay.
And then SU2 special unitary 2 U1 is the same U as electrons. So the QED1, and then you've got SU3 special unitary 3, which gives rise to quantum chromodynamics, basically quarks.
Okay.
So these kind of are the major players when it comes to defining the particles that we have.
Okay. Well, we can come back to that in a bit more detail, but I think that's useful because I've heard that thrown around fairly recently in a conversation, and I had no idea what was being spoken about there. So that's useful. Mm-hmm. Okay. How much further do we need to go with this? I suppose let's get into the Higgs. Let's for the last sort of 5-10 minutes. Mm-hmm. Where does the Higgs boson fit into all of this?
So, it turns out bosons associated with the weak nuclear force have mass. And, like I said, for example, nucleons, protons and neutrons, we know they have mass. So, but it turns out if particles interact via the weak nuclear force, and they have to have mass because we know they have mass, it turns out that violates the gauge symmetry. The symmetry is broken. Okay. So that's a problem.
Okay. Right, okay.
So what's going on here? We know these particles that interact with the weak nuclear force, we know they have mass. So what's going on here?
Yeah.
So as kind of described before, globally we know something to be true, but when you zoom in, a symmetry is broken. So what there needs to be a mechanism on a local scale that allows these particles to be massive, such that they can then interact with a weak nuclear force without breaking the gauge symmetry, without the symmetry being broken. So, we'll kind of take a bit of a step back and talk a little bit about potentials now, before we kind of get into the Higgs. So you can think of a potential. So I said it before. If I lift up this little pot above the table, it's got gravitational potential.
Yep.
Another way to think about it is thinking about it as potential wells. So
potential wells.
Like a water well that you might find in the field or something, right? So suppose this well looks like a bowl, right? So I've got a particle in the bowl in the potential well. So to get it out of the potential well, I need to give it a hard enough kick such that it's got enough energy to overcome that potential barrier.
Yep.
Right?
Yep.
Fine.
Okay. Yep. Yep.
And if it's in a bowl shape, when it's in equilibrium, it's ground state. Ground state and equilibrium don't necessarily need to be the same thing, but for this argument they are. When in equilibrium, in the bowl, it's going to be at the bottom of the bowl. It's going to be at the bottom point, the lowest energy state of that in that well. Fine. Suppose now, instead of a bowl, which is a nice potential well to be in, you have a bit of a wine bottle shape. The bottom of a wine bottle. So you've got like a W shape. So now there's kind of 3 points. There's the left trough of the wine bottle, the right trough, and then you've got the tip of the little peak. So those are 3 spots where you can be in equilibrium. If nothing kicks you left or right, a ball could sit in either one of those 3 spots and not really move.
Yep.
Okay. If the ball is on the top of the peak, if I give it a kick in a random direction, it's got an even chance of falling into the left trough or the right trough.
Mm-hmm.
So what can happen here is you get what's called a spontaneous symmetry break, where there are now 2 coexisting states that have an equal ground energy. So in a system, things generally want to fall down to the lowest energy state. They want to be in a ground state. Things don't want to stay energetic. Mm-hmm. So what happens now when you have a perturbation and you're in your unstable little peak of the wine bottle, you spontaneously get a breaking of the symmetry that allows a particle to simultaneously be in 2 different ground states of the same system. This is a bit of a problem. When this happens, when you kind of go through the calculation, you get these particles kind of come out of it, either side of the well. So in either trough, the left and right. These are called Goldstone particles or Goldstone bosons. They're massless, and they kind of exist because of this break in the.
Okay, so let me just interrupt there. So for our listeners that don't drink wine or that buy cheap bottles of wine that don't have the dimple in the bottom, we're talking about inside a wine bottle. A decent bottle of wine, you have a dimple in the bottom of the bottle. So we're imagining inside the wine bottle now. There's the little hill inside the wine bottle, which then you've got the trough all around that. So the particle could either be at the top of that little peak, or it could be either side of it. So you've got these 3 states. And so I was with you up to that point, but then I got a bit confused when you said about this new particle, did you say, that has to be introduced to explain the fact that it could be in either one of these 2 places of rest?
Okay, I wasn't particularly clear. So
okay,
when I'm saying a particle is on the tip of the sort of wine dimple, really what I'm saying there is a field which is in equilibrium in that part of the potential well. So the field is there. If I perturb the field, if I excite the field, then the field can simultaneously fall into 2 ground states. If we recall back to the start of the episode, an excitation in a field is a particle. So by perturbing the field in that equilibrium state at the top of the dimple, by perturbing it, then you can get two simultaneous ground states occurring at the same time.
Got you.
And
Okay.
because they're
I was
because
thinking classically, but actually you're talking. We're still in the same mode that we were at the beginning.
yeah,
Sorry, got you.
yeah,
Carry
easy
on.
mistake to make. But yeah, so because you've excited the field, you've essentially
Got you.
you're saying there is a particle there, but it exists in multiple ground states.
Got you.
So I guess thinking about it in terms of the phase change, obviously I've kind of given a 2D slice picture,
Yeah.
but
Yeah.
if I look bird's eye down, I guess down the whole of the wine bottle, it's a circle, right? You've got the top of the divot, and then you've just got a circle, which is a circular trough, right?
Yeah.
So relating back to the electric field of phase changes can be described as angular deviations. So if I say it's a 90 degrees phase shift, so degrees, like in a circle, when if I not 3 o'clock is 90 degrees from 12 o'clock, for
Got
example.
you. Yeah.
So because of the nature of how waves behave, this is a completely different topic now, but phase changes or phase shifts can be described in angular terms. So if I say
Okay.
fine. So what's occurred here, if you look at the bird's eye view, there is, for the same ground state, there is any number of angles that exist there. So that's why it's the kind of the symmetry is broken, because it's not just one ground state or another. There is however many angles in a circle, right? You could say 360, but if you take the points now, there's infinite, right? So that's why it's an issue. But anyway, okay, so this gives rise to massless particles. These are sections in the field. Cool. Okay, so we said before, for the symmetry to be conserved, the massless, so that the weak force can't interact with massive particles. Well, we have massless particles, problem solved. But this then contradicts the fact that we know that these particles have mass. So there needs to be an additional term to kind of come in here and give these Goldstone particles mass, such that then we can agree with what we're seeing. So the Higgs mechanism does that. The Higgs mechanism kind of tacks on to these Goldstone particles. A good analogy is kind of like, once the particles fall into this well, they're kind of rolling down treacle or honey, and then it's the honey there is the Higgs field that slows them down.
Yeah.
Because they're slowed down, they're slower than the speed of light, because massless particles all travel at the speed of light. So they're slowed down, and because they're no longer at the speed of light, they have to have mass. Therefore, this honey, this mechanism has slowed down these Goldstone bosons, given them mass. Therefore, we now have mass. The symmetry is resolved, and we now say the weak interaction does in fact have interactions with massive particles because of this Higgs field. So that's the kind of
that's the field that the maths tells us that there should be this Higgs field.
This correction term.
Yeah, and so the prediction is that there should be a particle associated with this, and that is this like one of the particles that you described right at the beginning in your little example of the ice skaters who hand one thing from one to another. This is a charge carrying particle, is it, or an interactive particle? Sorry, I'm getting my terminology wrong.
The Higgs boson is chargeless. It's neutral. There's no charge of the
Right.
Higgs boson.
Okay. No charge.
But yeah, so this.
But it's a force carrier. Is that right? It's a force carrier.
Yeah, force carrier maybe is a bit of a misnomer, but it's
okay.
Yeah, it's an interacting particle. It can interact. Yeah. So yeah, exactly. The prediction there is, because the maths says when you have this symmetry break, you get massless particles. Well, that contradicts what is measured. So there has to be, the prediction there is there's a missing piece, right? I mean, this kind of sounds awfully convenient, right? We've just essentially added in this magical field
Mm,
that just solves all of
mm,
our problems. And in this case, it's in terms of a scalar field. A field that mediates this magical
yeah,
mechanism.
yeah,
But if you recall again, if it's a field and can get excited, there must be a particle. So the Higgs boson is an
okay,
excitation in the Higgs field,
yeah,
which means if there's an excitation in the Higgs field, it has some physical
mm,
parameters, therefore
mm,
we can measure it.
yeah,
So, how do we measure it? Turns out not very easily, but if you have a budget of about 7.5 billion euros and
yeah,
17 miles in France and Switzerland,
yeah.
you can build
Nothing
a
to
big,
do in Switzerland. Yeah, yeah, yeah.
yeah, you can build a massive particle accelerator
Mm,
that spins particles around super relativistic, crazy high speeds, and then you get some wacky interactions, and then you can, yeah, you can see some interesting particles.
experimentally, you can actually you can see it.
Yeah,
Experimentally, you can find it through this this particle accelerator, which is fabulous, isn't it? And it's just a real, I suppose, it's a confirmation of the scientific method. Let's think about what should be there. This is what the theorists do. They hand it to the experimentalists who say, "Okay, I'll see what I can do," um, and then it's tested, and that's what's happened. I mean, there's arguments about the limits of that sort of approach and whether we've kind of reached the end of the line on that, which we won't talk about today. But I think as a way to understand what happened, I think that's fabulous, really interesting.
yeah. I mean, this is great. So this is in 2012 they discovered the Higgs boson,
Yeah,
and that was basically what CERN was built for. It's now also the LHC. The LHC. It's being used for other stuff now, but that's kind of that was the thing they needed it for.
yeah,
And in particle physics, the criteria to declare something a discovery is you need 5 sigma certainty. So what that means is, so 5 sigma in terms of a number. Hold on, sigma. Okay, so that means you are certain that that means the likelihood of that result randomly occurring by just
mm.
sheer fluke is 0.00002% likely.
So
And that,
0.00002. That's four zeros too after the
yes,
decimal point.
that's right. 4 zeros. So that's the likelihood of this result just being noise, which is obviously
Yeah,
very small, which means
very
it's
very unlikely.
yeah, so it's
Yeah,
99.99998%
yeah,
likely that it's actually accurate, and this is what you're seeing. So that's a
mm.
incredible precision to find. I mean, if you look at most experimental data, it's pretty hard to get 5 sigma certainty.
Yeah,
um,
yeah,
so
mm.
this was without beyond a shadow of a doubt, this is what they
Mm.
were looking at. And
Yeah,
since they've been able to reproduce this, this wasn't a one and done. This is you know, but 5 sigma certainty, extremely accurate. Yeah, 2012. That was a crazy big deal because that
yeah,
was a very big thing. I mean, the Higgs boson was theorized, I think, in the 60s or something. It was theorized ages ago. And the I don't know if this is true, but the kind of the story goes that when it was discovered, some interviewer asked Peter Higgs, I think his name was, the guy who
mm.
theorized the particle, oh, so now we've discovered the Higgs boson, how do you feel? And apparently he said, it's nice to be right sometimes.
Yeah,
um,
he's an English guy, isn't he? So
yeah.
typical British response, I suppose. Oh, very good.
Yeah.
Let's go and have a cup of tea and talk about it. I did see. So I'm old, a lot older than you. So I know you were around, but I was really interested in the news coverage at the time. I remember watching documentaries about it and seeing Peter Higgs at a big conference where they revealed these numbers and everything. It was quite touching, really. Seeing him, his life's work being proven, I suppose. Very few of us get the chance to be proved right in front of the world. So that must have been pretty amazing. Yeah. Okay. Good. Well, we've come to our hour, and that's a really nice place to, I think, finish it for now. Obviously, there's lots of questions unresolved that I now have, but I really feel like I've learned something. Um,
Cool.
and my questions might be stupid. I felt a bit stupid at times, but that's fine because it's only through asking those sorts of questions, isn't it, that we can understand it. So thank you very much, Thomas, for helping me to understand that. Good
No
stuff.
problem. I won't touch on it for too long, but yeah, there are
Mm,
obviously particle physics is a ongoing
yeah.
field of study. That there is some other stuff. I mean, we've not even talked about stuff like antiparticles or any other the kind of the big questions.
Don't worry. I want to get to antiparticles. Um, yeah, from the moment I watched the Star Trek episode about antimatter, I've always been fascinated by that idea. Yeah, let's pause it here. So let's call this part one. There's loads more to talk about,
Yeah.
and I think it's a really good grounding for me to come back to. Every time I'm going to talk to you about this stuff, I'm going to replay this episode so I can understand it, and then you won't catch me out with any more questions. All right, so don't forget, listeners, to subscribe to the YouTube feed. If you're listening on a podcast, then please subscribe and follow us on the podcast. Give us a review if you have the capability of doing that. That would be great. We've got some reviews, which is lovely. Thank you for doing that, those of you who have. And also the Facebook page. Don't forget to join. It's a free Facebook page, open to anyone at the minute. So join us and you can talk about this stuff. We do post things up on that. So, it's a useful little resource. Good. All right. Well, thank you very much. Thanks, Thomas, and see you next time, everybody. Bye.
Bye.